So we are here moving forward, going into section 8.3, where we're going to learn the law of cosines, which is going to allow us to complete side, 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 and side angle side triangles. And that's really what the objective is, solve those types of triangles. Okay. So as stated here, just, why not be extra redundant? When you know two sides and an angle, if the angle is not in between the sides, then you're in SSA, and that's a law of sines problem. If the angle is in between the two sides, side, angle, side, now you have a triangle congruence. The law of cosines is going to kick in, and it's definitely what you want to use when you know all three sides. Of course, we now would like to know what is the law of cosines. Okay, so the law of cosines looks a lot like the Pythagorean theorem, except you don't have to be in a right triangle. You just have angles, and you have sides across from them. Okay, and it doesn't matter what you pick. There's no such thing as the hypotenuse now because you're not necessarily in a right triangle. But this first line will look most like the Pythagorean theorem. C squared equals a squared plus b squared, but then all you have to remember is minus 2, then each of the sides that occurred here, and the cosine of the angle across from this side. So all three of these are really the same formula. Let's look at line 2. B squared is a squared plus c squared minus 2 times a times c, these two sides, times the cosine of the angle across from that, which is capital B. And the last one is really the same. A squared equals b squared plus c squared minus 2 times b times c times the cosine of this angle here. Okay. So I'll put up a separate video that says why the law of sines and why the law of cosines work the way they do, but for now let's just take it as a bunch of equations that we can use, okay? This is sometimes called the general Pythagorean theorem because it doesn't have to be a right triangle, but it's okay if it is. Let's see what happens if this is a right triangle, okay? So here's a right angle, and let's go ahead and say that's the angle A. Sorry, that should be the angle C because across from it will be the hypotenuse. And we'll call that C, that's standard. So here's A, and here's B, and here's little b. So if I use the law of cosines, I can write a squared plus b squared minus 2ab times the cosine of c is equal to c squared. But now c is a right angle, and the cosine of a right angle is 0, and that vanishes, and you end up with the traditional Pythagorean theorem. So sometimes this is called the general or generalized Pythagorean theorem, because it doesn't have to be a right triangle, although it does still work there, okay? It still works in a right triangle. Okay, so here are the law of cosines. As long as you know one of them, you basically know the others. Just have to remember that you can kind of switch around what side goes where and what angles goes where. You just remember that the side that has two squares in it also has minus twice times those sides and the cosine of the missing angle there. So let's use this to solve the following triangle. We're now given two sides and one angle. So this really nicely matches the following of all the versions of the law of cosines. There's one that involves the side A and the side B. Well, they all do, but specifically there's one that involves the angle C. So that's the one we're going to want to use. Okay, this one right here. So all three versions of the law of cosines involve the three sides. But they all involve a single angle. So if you only have one angle, use that version of the law of cosines. So we've got 4 squared, we've got 5 squared, we've got the cosine of 50 degrees. Okay, we can compute this with a calculator. If you don't have a calculator, that's fine. Okay, 4 squared is 16, 5 squared is 25, 16 plus 25 is 41. Then I have minus 2 times 4 times 5, aka 40, times the cosine of 50 degrees. So you can just call this whole thing here c squared, which means c is the square root of 41 minus 40 times the cosine of 50 degrees. And if you don't have a calculator, you can leave it like that. Heck, even if you have a calculator, you can leave it like that. Full credit right there. Okay, now that I know all three sides, okay, we can use a different version of the law of cosines to try to find one of the angles. Okay, so you might ask, can I use the law of sines? You can, but you'd have to be really, really careful about it, okay? So for example, I'm going to go back to the previous page, sorry. So we now know that this is about 3.91, okay? So if you were going to use the law of sines, let's try to find angle B. Okay, so I'm going to erase the work so that I have some space. Use this blank space now. Suppose we tried to use the law of sines. Here's what would happen. We'd say, okay, well, the sine of B over 5 is equal to the sine of 50 degrees over 3.91. And then you would go, okay. So now B is, sorry, the sine of B is 5 times the sine of 50 degrees over 3.91. Now maybe we pull out a calculator. I'm just going to open another tab and use Google. 5 times the sine of 50 degrees over 3.91, and we get 0.979. Okay. So the sine of B is 0.979. Okay, looking over at the left of the page now, there are two angles whose sine is 0.979. One of them is in 1 and one of them is in quadrant 2. Which one is correct? Maybe both. Who knows? Okay, the law of sines, remember, is only going to give you the quadrant 1 solution. The arcsine function, I'm sorry, which is why the law of sines is not preferred. If you use the law of cosines, you're going to end up taking an arc cosine. And remember, arc cosine gives you one angle either in quadrant 1 or quadrant 2, which means it's perfectly suited to find angles and triangles with no ambiguity. Okay. So when you're trying to find missing angles using lots of side lengths, use the law of cosines. It looks like it's worse work. A lot of people find the law of sines preferable. It looks simpler, but the ambiguity in the arcsine function is going to throw you off. Okay, so we're going to use the law of cosines. So to find angle A, we're going to use the version of the law of cosines that has angle A in it. Remember, at this point, we already know all three side lengths. So we're going to solve for angle A and plug in the side lengths that we know, 5, 3.91, and we end up with A as the arc cosine of this. And remember, arc cosine gives me something in quadrants 1 or 2, in other words, between 0 and 180 degrees, and it's not ambiguous. It's perfectly suited to find angles of triangles. And this works out to be 51.6 degrees, and there's no two options about this at all. Similarly, you do the same computation using the law of cosines version for B, and end up with B as the arc cosine of all this mess, which works out to be 78.4 degrees. Of course, since we already knew two angles, we could have just said 180 minus the missing, minus the two angles we already know gives us the missing one. So this is kind of overkill, but just to practice, we see that you can use the law of cosines to find missing angles. Okay. It is a way to double check. I mean, we had already found 50 was what was given to us, and we had just found 51.6. So sure, using the fact that all three add up to 180, you would find this, but then you might want to double check your work by just doing the law of cosines again. And since this also matches the same result, you can be confident it was correct. All right, here's another example. Notice I don't have any angles. We're just given three sides, but since side, side, side is a perfectly legit triangle congruence, hopefully we can find all the missing angles. And we can. Use the law of cosines just over and over and over again to find each angle. It doesn't matter which one you find first. They're all pretty much the same at this point. So for example, if we try to solve for cosine of A, remember we'd start off with A squared equals B squared plus C squared minus 2BC cosine of capital A. Then what you would do is you would move the cosine term over, you'd subtract this, and you would divide by 2BC. And you'd end up right here. This is work that was done in the previous slide, so hopefully you worked it out then. But now we would just take the arc cosine. Okay, we know all the values of the side lengths, and so take the arc cosine of 5/7, 44.4 degrees. Great, we found one of the angles. Do it again to find, for example, angle B. Okay. All you would do now is you'd start with the version that says B squared equals A squared plus C squared minus 2AC times the cosine of B. Solve this for cosine of B and you'll get right here. Then you plug in the known values, take an arc cosine, and great, we found that angle. Now I know two angles, so I can quickly find the third. Okay, since we found an angle of 44.4 and an angle of 34.0, We just, subtract each off. The third angle must be 101.6, and now we have found all of the angles, and we're done. We found all the angles and all the sides. So that's a quick little introduction to the law of cosines. Okay, so it's not that big of a deal once you get used to working with these squares. It looks like a more inconvenient formula than the law of sines, but honestly, because the law of sines might require you to use an arc sine, which is ambiguous because it will only give you a quadrant 1 solution, it won't give you a possible quadrant 2. If you have the option of using the law of cosines and you're comfortable doing it, I would recommend going that way. In the next video, we're going to come back into problems that look like this. This matches the form of problems on the final exam. It's just a chart with some numbers given, and you have to compute the rest. So come on back to that in a minute, and we'll work through them.